Hi everyone. Today we will see what is the rule of 13 and what is its role in the structural elucidation. How we determine the structure of compounds. In the structural determination of unknown compounds, we can use the different types of methods, and among these one of the method is the chemical methods. In the chemical methods, we can determine the ring size of the unknown compound if the compound is a cyclic structure. Otherwise, we can determine the presence of methyl groups in the structure, and we can also identify the presence of functional groups in the unknown structure by using these chemical methods. But nowadays, we can use the modern analytical techniques, and particularly we can use the spectroscopy in order to identify the structure as well as to assess the structural features of the unknown compounds. For example, we can use the NMR spectroscopy, which gives the structural information and it acts like a fingerprint spectra. And we can also use the mass spectroscopy, where this technique will give the fragmentation pattern of an unknown compound. And we can also use the IR spectroscopy, which is again giving the fingerprint spectra of every unknown compound, which can be matched with the already well-known compounds. So in this way, we can use any of these spectral techniques in order to assess the structure of the unknown compounds. But here we will see how we are going to use the mass spectroscopy, where we can use the rule of 13. So role of mass spectroscopy in the structural determination. So what is mass spectroscopy? The mass spectroscopy involves the simple fragmentation of an unknown compound into the different types of fragment ions, and we can assess how many types of ions are going to be produced within the mass spectroscopy. For example, if an unknown compound is having a molecular weight of M, then it is undergoing the ionization so that it is going to give the molecular ion M plus 1 electron. But this molecular ion is having some energy, so it cannot be stable and it can undergo the further fragmentation such that it is coming to a fragment ion M1 plus and M2, which is a neutral fragment. In this way, fragmentation can be continued until the stable fragment ion is going to be produced. So here in the mass spectroscopy, the detector will detect how many types of ions are going to be produced and what is their M by Z ratio, where M is the molecular weight and Z is the valency of the ions. So Z is the valency of the ion, that means it is the positive charge of the ion. But here most of the times we focus on the univalent ions, so M by Z simply indicates the molecular weight, where Z is equal to 1. For example, let us take the mass spectra of an unknown compound. So here the x-axis is the M by Z ratio, which simply indicates the molecular weight of the different types of fragment ions. And y-axis is nothing but the abundance, the relative abundance of the ions that is going to be produced within the mass spectra. For example, for an unknown compound, we got the one of the peak with M by Z ratio 84. That means it is having a molecular weight of 84. And another peak is at the 55, and we have seen the few of the other peaks like this. Now here, what is the peak corresponding to 84 indicates? So what are the peak which is going to lie at the right side of this mass spectra? Mostly it indicates the molecular ion peak. And we can also sometimes observe few of the quasi-molecular ion peaks which are greater than this molecular ion peak, but these peaks will have less intensity, so they will have the less height, so we can easily detect which is the molecular ion peak. So for this example, 84 indicates a molecular ion peak. And here in this mass spectra of this unknown compound, we can observe a tallest peak which is called as the base peak. That means the molecule is undergoing a fragmentation to give a stable fragment ion which is having a molecular weight of 55. Now by knowing this molecular spectra of an unknown compound, we know the different molecular weights of the ions produced in the molecular spectra, and from this we can assess the structural features of the unknown compound. For example, here what is the molecular ion peak is the 84, and here we can calculate the index of hydrogen deficiency by using the rule of 13. Then we can assess what may be the possible structural features of this unknown compound. Now let us see the calculation of IHD with the molecular weight. So whenever the molecular weight is known by the mass spectroscopy, we can apply the rule of 13 in order to assess the IHD value of the unknown compound. The rule of 13 is a simple calculation where we have to divide the molecular weight by 13. And when we are going to divide, we will get the quotient as well as the remainder. the quotient can be represented as the N value and remainder as the R value. Then we can write the molecular weight as N and R by 13. So this is nothing but N plus R by 13, where N is the quotient and R is the remainder. Then we can calculate the IHD value as IHD is equal to N minus R plus 2 by 2. So let us take one example here. Let us take the first example, cyclohexane. Now let us calculate the IHD value by all the methods available. So this is a cyclohexane having the molecular formula C6H12, and if we compare with the standard molecular formula, it will be C6H14. So the number of hydrogens less is the 2. So IHD value will be 2 by 2, that is equal to 1. So cyclohexane is having the IHD value as 1. And again we can see by structure it is having one cyclic ring without any pi bond, so IHD value is again 1. And now let us check by the molecular weight. So the molecular weight of this cyclohexane is 6 into 12, because carbon is having the atomic weight as 12 and hydrogens are having the atomic weight as 1. So 6 into 12 plus 12, which gives the 84. Now let us divide this 84 by 13. So when we divide by 13, we will get the 13 into 6 plus 6, which can be written as 6 and 6 by 13. So 13 into 6 is nothing but 78 plus 6 is nothing but 84. So this can be written as 6 and 6 by 13. So now here the quotient N is the 6 and remainder R is again 6. So if we calculate the IHD value, the IHD is equal to 6 minus 6 plus 2 by 2, which gives the 1 value as the IHD. So now you can easily check that if we calculate the IHD value by seeing the structure or by seeing the molecular formula or by taking the molecular weight, we will get the same value. But which formula should be used, it depends on the data we have. Suppose we have the structure of the compound, we can check the number of cyclic rings and the pi bonds so that we can get the IHD value directly. Otherwise, if we have the molecular formula, we can compare the molecular formula with a saturated open chain compound and we can see the number of hydrogens that are less, and when we divide this value by 2, we will get the IHD value. But whenever the molecule is having the heteroatoms, we have to use the corrected molecular formula. Whenever the molecular weight is given, we have to apply the rule of 13 and we have to divide the molecular weight by 13, so that we have to use the quotient and remainder to calculate the IHD value with the formula N minus R plus 2 by 2. Now let us see the assessment of molecular formula of unknown compound by using rule of 13. So molecular weight is given as 84 for this example. By applying this rule of 13, we can write the 84 as 6 and 6 by 13. So here the quotient is 6 as well as the remainder is 6. For this unknown compound, we can write the molecular formula as CnHn plus R, where N is the quotient and R is the remainder. So for this compound, the molecular formula will be C6H6 plus 6, because N is equal to 6 as well as R is equal to 6. So this is nothing but C6H12. So the unknown compound is having a molecular formula C6H12 whose molecular weight is 84. So when we know the molecular weight of this unknown compound, we can easily write its molecular formula by using the rule of 13. And suppose if the compound is having a heteroatom like the nitrogen, then what will be the molecular formula? Because nitrogen is having an atomic weight of 14, so in order to add the nitrogen, we have to deduct CH2, because carbon is 12 and hydrogen is 2, so total is 14. So we can add the nitrogen and we can deduct the CH2 from this molecular formula, so it will be C5H10N. So from C6H12, we have deducted 1 carbon and 2 hydrogens, and we have added 1 nitrogen. So the molecular formula will be C5H10N. Similarly, if we want to add the oxygen, since oxygen is having the 16 atomic weight, then we can deduct the minus CH4, because carbon is 12 and hydrogen is 4, so total is 16. So then the molecular formula becomes C5H8O. And similarly, if we want to add the fluorine, fluorine is having the 19, so we can deduct by 1 carbon and 7 hydrogens. So it becomes C5H5F. In this way, we can write the possible molecular formulas for the unknown compound if we know its molecular weight by applying the rule of 13. And we can also assess whether the compound is having the nitrogen, oxygen, fluorine or any other atoms by again seeing the spectral features as well as by using some chemical methods. So by combining all the data, we can determine the possible structure for an unknown compound. Now let us see the structural determination of the unknown compound with the use of its molecular formula as well as the IHD values. Suppose if the molecule is not having any heteroatom, then for the molecule having a molecular weight 84, the molecular formula will be C6H12, and for that we can write the different structures like this. So one of the structure is this 1-hexene, and another structure is methyl cyclopentane, and another one is the ethyl cyclobutane, and another one is the cyclohexane. In this way we can write so many structures for a given molecular formula. So already we have seen this example in our previous video. And here we can use this information along with the mass spectra, and we can assess the possible structure for the unknown compound. For example, if the compound is having any cyclic structure like the cyclopentane, cyclobutane or cyclohexane, within the mass spectra it will give a peak like M-29, where M is the molecular weight. So if the molecular weight is 84, 84 minus 29, that becomes 55. So it will give a peak at the 55. Similarly, if the molecule is a alkene, again it can give the peak at the M-29. Along with this peak, it will also give another peak at the M-41. So if both of these peaks are present, then we can say that it may be a alkene. Cycloalkanes also give the M-41 peak, but their abundance is very low compared with the alkenes. So just by seeing the type of peak as well as its relative abundance, we can assess what may be the structural feature of the unknown compounds. Now if we go to the previous example, we got the mass spectra like this. So here the 84 is the molecular ion peak, and what about the 55? So this 55 indicates simply M-29. M molecular weight is 84, then M-29 will be 55. So here this spectra indicates a peak corresponding to M-29. So it may be a cycloalkane or it may be alkene. And here suppose we got another peak at 43. What this 43 peak indicates? So 43 is simply M-41. And we can also see that the abundance is somewhat significant in this spectra. That means it may be an alkene, it may be 1-hexene, 2-hexene, 3-hexene, whatever may be. That means we can say that it is having an alkene in this compound because it is giving a M-41 peak with some significant abundance. And again we can confirm this by using the IHD value. So for this compound the IHD value should be 1 because it is having 1 pi bond, and already we have calculated the IHD value by use of rule of 13, where we got the IHD value as 1 for the molecule with molecular weight 84. So in this way, by using the mass spectroscopy, we will get the different types of ions at the different molecular weights, and for each molecular weight we can assess the possible structure by using the rule of 13. So rule of 13 can be used to determine the molecular formula of unknown compound, as well as it can also be used to identify the index of hydrogen deficiency. By combining all these, we can assess the possible structures for each type of fragment ion. By combining all these data, we can assess the structure of the unknown compound. So that is the use of the rule of 13 in this mass spectroscopy. So rule of 13 is a simple way of calculation of molecular formula, where we have to divide the molecular weight by 13, and then the molecular formula will be CnHn plus R, where N is the quotient and R is the remainder. Similarly, the IHD value can be calculated as N minus R plus 2 by 2. So that's about the rule of 13 in structural elucidation. If you like this video, please subscribe to our channel, share this video with your friends, and post your valuable comments in the comment box. Thank you for watching this video.